All right, folks, we're going to take a look at the Chapter 4 notes. This is also known as the Newton's Laws of Motion notes. And when you guys look through this on the front page of this, if you were able to print this, you're going to see a list of vocabulary. And all I want you to do for this is you can use any online resources, or if you do have a paper copy of something like a physics book or a science book or encyclopedia or something like that, you can certainly feel free to look up the vocab there and just write down and define the terminology in that location. Okay, so that's all on the front page, so I'm not going to go through any of that with you guys. However, if you flip over to the second page, the very first topic that we're going to take a look at is Newton's first law. We're going to go through all three of the laws in these examples, and I have just a few example problems for each one, and at the end we'll talk a bit about the application of these laws, and that's going to be about it. So please follow along, copy down as needed, and if you guys ever have questions, you can always feel free to email me. So here it is. Newton's first law. This is also known as the law of inertia, and the reason it's called the law of inertia is because the whole law itself basically is kind of describing a characteristic of mass and force or motion. So when we look at this, you won't see a mathematical equation involved, which with a lot of mathematical or scientific laws and equations, there'll be some sort of a, multivariable equation that'll go along with it. In this situation, it's more conceptual. So Newton's first law states that objects at rest will remain at rest, and objects in motion will remain in motion unless acted upon by some outside force or some net force. So this is 100% related to the amount of mass in an object. And the difference between mass and weight is a very critical thing that we'll talk about as we go along. But generally speaking, mass is how much matter is in an object, and mass does not change dependent on where you are on our planet, or maybe even take this thought process to space. If you're on a different planet or some other body in space, like say the moon, where the gravity, attraction of gravity of mass toward other masses is different, the mass of an object will not change. Its weight, however, will change. And when we get to Newton's second law, we'll talk a little bit more about what weight actually is. So, reading through some applications of this, in example 1, it says an object is resting on a flat surface. Can the object ever start moving if a force was never applied to the object? Well, this may sound pretty straightforward, but the important idea here for you to understand here is that no, it can never start moving unless you apply a net force. And a net force doesn't just mean one or two forces that, like, say, cancel each other out. A net force means there's an imbalance of force. So when you are sitting motionless in your chair, gravity's pushing you down in your chair, but there is also a force pushing you up, which often is called the normal force. Now, it doesn't mean there are not forces present. There's a force pushing down and a force pushing up, but if those forces are equal and opposite, the net force, the total force acting on the object, is zero. It's kind of like a tug of war. If both people are pulling in opposite directions with the same force, the result is nothing. Things wouldn't move. So it's the same idea with like a resting object on a flat surface. Don't think that there's no forces anywhere. It's just that the forces that are present are balanced. And the idea of a net force, again, that's the summary of all the forces. For example 2, it says there is a spaceship coasting through space at 20,000 meters per second. It is away from any significant gravitational force. How fast would the object be going if it never turned on the engines or encountered any other objects? Well, very similar to example 1, this object would continue to keep moving at this very high rate of speed because it's in motion and there's nothing there to slow it down. There's no air friction, nothing else. It would continue to go at 20,000 meters per second because it is moving and it has inertia in motion. There could be inertia not in motion, there could be inertia in motion. It does not want to change from what it's doing unless some other force acts on it. All right? So that's basically all of Newton's first law. For Newton's second law, the first thing you'll probably see here is that there is a mathematical equation involved, and it only has three variables. The F stands for force, the M is mass, and the A is acceleration. We measure this in newtons, which these are Newton's laws, and kind of funny that they actually name the measurement of force as newtons. Now, with most equations, we talked about velocity, we've talked about accelerations, you've had like distance and time or change in velocity over time. you can always rearrange these equations to solve for any three, which will be helpful because not always will we be given a mass and an acceleration and asked to find a force, where you could just simply multiply these two numbers together to get this. They may give you a force and a mass and ask you to solve for acceleration. If that was the case, we can rearrange this equation to look something like this. Acceleration would be force divided by mass, because if you think algebraically, if we started with the force on the left-hand side and we wanted to move the m over here, in essence, you divide both sides by m, and you get F divided by m equals A, which would be this equation. If we wanted to solve for mass, we can do a similar thing. We would divide both sides by A. So if we wanted to solve for m, you would do F divided by A, force divided by mass, force divided by acceleration would give you mass. So when we're solving these equations, I always try to tell you to do three basic things. One, you're going to read the problem. We're going to list the variables. And then two, you're going to, once you know what the unknown is and what we're trying to solve for, you're going to determine which equation it is that you want to use. And then the third thing you're going to do is actually plug the numbers in and either be dividing or multiplying the variables that we got. So here's example 3. It says a hockey puck with a mass of 0.5 kilograms. So we know that this is a mass, so I'm going to list this right now. 0.5 kg is accelerated at a rate of 22 meters per second squared. So they're telling me now this is an acceleration, so I'm going to say, okay, the A is equal to 22 meters per second squared. How much force is applied to the object? So the unknown here is force. So we do not know what the force is. Well, looking at the equations that we have, they give us m, they give us a, they ask for f. So the way you choose the equation is you look and see which variable you're trying to solve for, and whichever one of these has it isolated by itself is the one that you use. So since we're solving for force, we're going to use this equation. If force is equal to m times a, now we mathematically know what to do. M is 0.5, and acceleration is 22. And while we would normally keep all of the variables in here for the simplicity of things right now, we're just going to multiply things out. 0.5 times 22 is the same as a half multiplied by 22, and half of 22 would give you 11, and we know that the units are newtons. For example 4, it says a speeding car is traveling too fast when a deer runs out in front of them. If the car has a mass of 2,000 kilograms, so I'm going to write this down because they just stated that there's a mass of 2,000, and the brakes are applied for a frictional force of 500 newtons. So this frictional force is the same thing as the force. It's just going to be like a negative because it is slowing down the car. What would be the rate of deceleration? So notice here they say deceleration. That's the same thing as a negative acceleration. So the unknown is the acceleration. Look at the equations that we have. Acceleration is force divided by mass. So there's your F divided by m. Plug in the force, which is negative 500. The mass is 2,000. And when we divide that out, that ends up being about a quarter, which is the same as 0.25. And the units for acceleration, like we had used before, are meters per second squared. And that, by the way, is not a very fast acceleration. That's pretty gradual. The acceleration of gravity, if you were to just take an object and let it fall to the ground, would be nearly 10. So much greater than that. Newton's third law. This one is also a statement, but it's applied very commonly. You'll commonly hear this applied when they talk about collisions or propulsion, but it really holds true for any time a force is applied. Sounds simple, but it says for every action there's an equal and opposite reaction force, and this basically says that forces act in pairs. So really, if a force is present, there had to be something the force was applied to and something that kind of absorbed the force. It would be like saying you walked over to the wall and pushed on the wall. One might think, okay, how are there two forces there? Like I walked over and pushed on the wall. Well, The only reason you didn't go through the wall or walk through the wall or be able to push your hand through the wall is because the wall pushes back on you. So forces are equal and opposite. So if I push on the wall with 10 newtons, the wall pushes on me with negative 10 newtons. The wall does not move. The wall does not accelerate. There's no change in motion. There's almost like infinite inertia with the wall. So the net force ends up being 0. So with that said, let's look at the examples. And they just want us to make a very simple free body diagram, which is a simple sketch of what's happening in this scenario. So it says draw a free body diagram of a block that has a mass of 10 kilograms. So I'm just going to simply draw a square here, and I'm going to just say that it has a mass of 10 kilograms. It's sitting motionless on the floor, so I'll just say that it's sitting on the floor. It says be sure to include your f of g and your f of n. So we haven't talked about this totally, but similar to the scenario where you're sitting in your chair and nothing's moving, there's a force pushing down, there's a force pushing up. The force pushing down is typically where I try to tell people to start. This force of gravity, this f of g, this is present in all objects with a mass that are within a gravitational field. Now, here on Earth, and we'll start with scenarios on Earth because that's going to be our most common examples. On Earth, we're always under this constant acceleration that's approximately 10. It's 9.8 meters per second squared. Almost everywhere you go, it varies slightly with altitude and how far you get away from the center of the Earth. So that, I always say start with that. Since this object's sitting on the ground, we know that the force pushing back up is equal and opposite. So this would be considered the normal force going down this way. Now, if I wanted to get specific with this, I could actually determine what these forces are numerically. We know that force is equal to mass times acceleration. We know in this situation the mass of the block is 10, and the acceleration of gravity on Earth is 9.8 meters per second squared. So if I multiply this out, this is going to give me 98 newtons. Now, I don't necessarily have to recalculate this on the bottom, but we know through concept that the forces are equal and opposite. So if I'm saying the force down is, let's just say it's a positive 98 newtons, I know the force going in the other direction is a negative 98 newtons, which makes the net force 0. You could call the downward force negative and the upward one positive if you want. That's your choice when you make the diagram. It is common to have the gravitational force labeled as negative, but for here, we'll just say that that's the one is positive and the other one is negative. For example 6, this one says a baseball player swings a bat, making direct contact with it. The ball experiences an abrupt force of 12,000 newtons. How much force does the ball exert on the bat? Well, I'll label this out really simply. The bat onto the ball, they said, was equal to 12,000 newtons. We just switch this around and we'll just say the ball onto the bat, which is just stating it in reverse, would be equal and opposite. So instead of being 12,000, it would be negative 12,000 newtons. So if you were ever to swing a bat and you hit a baseball and, like, say it was a wooden bat and you weren't wearing gloves, and you feel that kind of sting in your hand, that would be the exact reason as to why you feel the sting in your hand, because all that force from the ball is going right into your hand. All right, so we flip over to the back. We're going to talk a little bit about friction. And the reason we talk about friction when we talk about one-dimensional motion is in the real world, this is most commonly some of the forces that oppose motion. So friction always opposes motion. So if you're pushing something forward, friction's going backwards. If you push something to the right, friction's going to the left. If you're driving your car down the road with the front of your car facing down the freeway, the frictional forces are pushing backwards against the front of your car and wanting to slow you down. Hence the reason your automobile needs to keep running and applying energy and work into the car to keep it moving. Unlike the spaceship scenario at the beginning where we said, hey, if you're in outer space and you turn off your engines and you coast forever and ever and ever, that's because in space there's not really friction because there's no material there to collide with your object and slow it down. So I'll go through some of these quickly and we'll move on from there. Frictional force is often represented with a capital F, which most all forces, again, are. You will see the subscript, the smaller abbreviations underneath here. These are some of the common ones, and you'll see down here I just put other, and I'll list some examples of what those might be. But generally speaking, these are your common subscripts. F of F, so the force with a lowercase f underneath it, is typically known as your force of friction. So again, if you're pushing something to the right,